important concept, invariance concept. In problem solving, sometimes, not always, sometimes you need to use this concept to help you answer several questions. All right. First, let's review this concept. So last time, after we work on our data, 2 columns of data, we do observation. After we complete, everything. So we want to find some common rule. All right, yeah. Here we found the size. When we look at the size part, we pick the side number. So n. We pick the side number n. Then we look at the number of squares. That number, how do we get number of squares? We use the horizontal counting and the vertical counting, right? Yeah. Here, look at, we count horizontally. This is the horizontal counting, okay? Yeah. Then we can do the same thing on the vertical counting, okay? Yeah. Here, we use the one side counting, okay? Horizontal or vertical, but only one dimensional counting. Yeah. That number is the n number, right? Yeah, that number, n number. Yeah. Now, these 2 numbers adding together, m plus n equals a constant 9. And this equality holds for all the sizes. That's the reason we call it invariance property. This is the invariance property. This is quantity provides us invariance property. What's the benefit? Next step, you may ask me why we need this invariance, right? Why it is useful? Yeah, it could be very useful. Yeah. First, this invariance property, it gives us global rule. This rule holds globally everywhere, right? So it's a global property. It's not a local property. Only holds in some, small region. It holds. No, it holds globally, everywhere. Yeah, that's a nice property. Okay. All right. Then, why it is useful? Yeah. So let me explain why it is useful. Yeah. So let's continue. Yeah. So we understand the role of this invariance in problem solving. So invariance usually provides us critical property or insight of the problem. Yeah. Yeah, because this property is so important. Yeah. Sometimes we rely on this property to help us figure out some very difficult, some questions very difficult to answer. Yeah. We need this property. Yeah. All right. So invariance, its first usage of this invariance can help us keep track of the data. One common usage, keep track of the data. So what's that, keep track of data? Yeah. We know, in general, the given data is very messy, right? Very messy means hard to organize. The given data is very messy, okay? Yeah. Distributed in many different ways, and it's hard to get our data organized. Yeah. All right. Then under that situation, if we want to keep track of the data, yeah. So if we want to do some special counting, it's not easy. Yeah. Let me give you one simple example to understand this point. The example. Let's consider a generalized chessboard. Yeah. 100 by 100. We can use this same way drawing the standard chessboard, but we extend it to 100 by 100. How about that? It's a generalized chessboard. Right? All right. So with this larger chessboard, yeah, definitely it's hard to draw on the paper, right? Yeah, if you draw 100 by 100, it's not that easy, right? Yeah. So you can only use your imagination. Yeah. In your mind, you draw that 100 by 100. Okay? Yeah. Right. But you need to answer questions. Okay? The question is, how many squares are of the size 37 by 37? By your answer what?
73 by 73.
73 by 73. Any other different answer? He said 73 by 73. 75 by 75? Only 75? Oh, yeah.
74 by 74.
Good. 74 times 74. How do you get it? Can you explain? Other students?
From the previous chessboard,
Uh-huh.
you are always forgetting 9 as the sum for the sides.
Right.
And here we have 100
Yeah.
sides, and it's plus 1, which is 101, and then we subtract 37.
Yeah.
We get how many?
Yeah. Perfect. That's perfect answer. Okay? You only miss one small one, right? Because you need to add a 1. The side number, you use the side number directly, 100, right? But he observed closely. He noticed it's not exact side of the chessboard. It's the side of the chessboard plus 1. Yeah. But you are very close. Yeah. See? Think about, if you do not use the invariance, how do you find the 74? Yeah. You use the invariance concept, right? Yeah. Help us keep track of the data. Because if we do not use the invariance property, how do you keep track of that 37 location, right? Yeah. If you do the counting in your mind, too hard, right? Not that easy, right? How do you draw in your mind, 37? Almost impossible. Okay? That's the first usage of this invariance. First usage. Yeah. Definitely, we may have several other usages. Yeah. First usage. Yeah. The second usage. Yeah, but I won't give you today. Okay, I won't give you today. I will give you sometime later. Yeah. I will give you a very challenging, interesting puzzle question later, sometime later. Yeah, but not today. Today we have a lot of things to do. Okay. Sometime in an appropriate time, yeah, I will give you another puzzle question related to invariance property. Yeah. Why it is so useful? Okay, yeah. All right. So I hope, yeah, in this our first example in this class, you notice the importance of this invariance. Later, in many of our later questions, we need to use it. When we need to keep track of the data, we need this invariance property. Okay? Yeah. All right. So let's continue. Yeah. 64, not 70. Yeah. Okay. Yeah, 64. All right. Yeah. So, right. Yeah. And usually how to find invariance, it's pretty hard. Here we do experiment, we do observation, right? Yeah. Experiment, observation. Yeah. So for this question, it's not that hard, Yeah. Then, in the question I mentioned, I will give you a puzzle question. You need to find invariance. That one, it is much harder. Yeah. But very interesting, very challenging, interesting. Yeah. Also on the chessboard. It's a chessboard puzzle question. All right. Yeah. So then, now the last step, we need to complete the computation work. We need to find the final number, right? Counting number. Yeah. Yeah. So that's the final counting number. The sum of squares of these 8 consecutive integers. Although you can use calculators, you can punch the keys on your calculators, you can find the final number. Okay, yeah. I allow you to use online calculator, type, Wolfram Alpha, you can type these numbers. Yeah. All right. Yeah. But is there a formula? Because if I ask you the same question on 100 by 100 chessboard, then it's hard to punch the keys on the calculator, right? Yeah. Yeah. Right. Yeah. So for the 100 by 100, you want to get a formula to calculate it, right? Yeah. Existing formula to calculate it. Yeah. So then we want to consider the general case, n by n, the general case. So we want to find a summation of these n consecutive square of integers. Anyone knows the formula clearly, yeah, without doubt? Without doubt. Okay? Not guessing, because it's very hard to guess. Very hard to guess. Yeah. Look at this formula. How about that? 1/6 times n plus 1 and times 2n plus 1. How about that? Yeah. You cannot guess it. Okay? Yeah. Now, you plug in 100, you get that. Sum of squares of 100 integers, right? N equals 100. You find the answer. Okay? Yeah. More efficient. Yeah. Oh, some of you may like to write a computer program to calculate sum of squares, right? Yeah. But still, not as good as this formula. Yeah. Yeah. All right? Yeah. Do the summation. Yeah. So we complete this question. Yeah. So you can see we have learned several things. Yeah. What do we learn in this first example? Yeah. First thing, the idea, organize the data, importance, how important to organize our data in different categories, right? So that's important. Yeah. One idea. Another invariance concept, to keep track of the data, important. Okay, yeah. Yeah. The third, this last summation formula. Third. At least we learned these 3 things from the first example. Okay, all right. Here I do the summary. Okay, yeah. The first one, that invariance property, this one. Okay, all right. Second one, this summation formula. Okay, yeah. So later, we may have some other questions. We need to apply this formula, but you need to do some manipulation. You need to do some manipulation. For example, if I ask you to calculate 2 square plus 4 square plus 6 square plus ... plus 2n square. Can you calculate? Can you find it? Expression. The first n consecutive positive integers. How to find sum of these n squared, these first n consecutive positive even numbers, not even. 1/3, only 1/3. Other students, some different numbers. What do we need to multiply on this formula? By what? By n? Yeah. By what? By 2? Yeah. Other students, different number. Square of 2. Yeah, that's great. Square of 2, 4. Oh, sorry. Oh, what's wrong? Yeah, the reason is we can factor 4 out, right? Can we factor 2 square out? After we factor 2 square out, that's 4, we have 1 square, 2 square, 3 square left inside n squared. So we can use the original formula. Yeah. 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 Try to do the manipulation like this. Okay? Yeah. Yeah. Another example. Yeah, let me ask you another example. If I ask you calculate 7 square plus 8 square plus 9 square consecutive squares plus 25 square. How to calculate this number? But start from 7 square, not start from 1 square. How to calculate? How to use this formula? We need to use the formula. Do not use calculator, all right? Use the formula. How to modify the existing formula to get the answer. Good, good, yeah. His idea, right direction. Yeah, right direction. Yeah. I hope you understand. He said, because we have the formula starting from 1 square plus 2 square plus 6 square, right? We have a formula, okay? Yes, starting from 1. But you cannot add this part for free, right? That part you cannot add it for free. You need to take away. After you add it, you need to take it away to get it balanced, right? The whole thing must be balanced, okay? You cannot add anything free, right? To make it balanced, how about you subtract the same thing? How about that? 6 squared. Subtract the same thing, yeah. But this sum of squares, you can apply the existing formula, right? Yeah. The parenthesis part, you can apply existing formula second time, right? Take subtraction, you get the answer. How about that? Okay? Yeah. Here, I give you 2 very simple examples. For you, you need to modify. Yeah. You need to find a smart way. Okay? Yeah. Simple. These 2 very simple, straightforward. Smart way to manipulate existing formula to get a final answer. Think about that. We need to do things like this in problem solving. Yeah. All right. You need to modify the existing result to solve many different problems. All right, let me give a last one for you practice. Not doing here, okay? The last such example. So you can practice at home, but not here, okay? All right. Let's start 11 squared, okay? 11 squared, but not consecutive square. Skip one number plus 13 squared. Okay? Yeah. but the consecutive odd integers, all right, plus 15 squared, consecutive odd integers, okay, dot, dot, dot. The last one, okay, let's say 99 squared. How about that? Okay. This time you need to, do some more complex manipulation on our given formula. Okay, that's in formula. But this time, you need to do several things, not just one thing. You need to do several things, several times, apply the formula several times to find the final answer. Okay, all right. Yeah, think about it. Practice, question, like this. All right. So we finish part A. So let's move to part B. New topic. Part B, the topic, efficient polynomial evaluation. Yeah. This problem is very interesting and not hard to understand because we know what is a polynomial. So we are familiar with the polynomial concept. And we also know how to do polynomial evaluation. But the problem is, if your polynomial evaluation is efficient or not. That's the higher level question. Is it efficient? It may not be efficient, right? Yeah. So we want to answer that question. Efficiency regarding the computation efficiency, that question. All right, first, let me give you the problem, our computation problem. Yeah. I treat it as our first computation problem. Okay, yeah. Yeah. The title, evaluate a polynomial. The question, our data, given data is a polynomial data this time. But the polynomial, so you have a sequence of coefficient, right? Yeah. A0, A1, dot, 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 AN. Yeah. So this n plus 1 coefficients here. So we call it, this is a degree n polynomial. Okay? It's degree, the highest term, this is the highest term. Or we call it leading term. Yeah. Leading term. When we say the leading term, we need to assume not equal to 0. A sub n cannot be 0. That's the leading term. Okay? Yeah. All right. Yeah. So these n plus 1 coefficients must be given. Let's say floating point numbers. Okay? Floating point numbers. This topic, I will use this topic as our first programming project. In our first programming project, these coefficients will be integers. I do not use floating point numbers. I use integers. Yeah, but in this question, we use floating point numbers, coefficients. All right. The variable x can change every time. Yeah, it's a variable. Yeah. So you can, because when you want to evaluate a polynomial, you need to determine the x value first. Then you plug in x value so you can calculate and find the value of the whole polynomial. All right? Yeah. The question, how to find p of x efficiently? Because our main focus is at the efficiency of the method. Yeah. Because everyone can find the answer correctly, right? Yeah. Using computer, everyone, you can find the answer correctly. Yeah. But the question is, can you find it more efficient? So that's another question. Correctness is one question, but efficiency is another question. Okay? Yeah. All right. Here, I give you the reference. So the material I select from section 6.5 on page 233. Yeah. So here, although I jump to section 6.3 this early, the reason is, first, this problem is interesting but simple. We have enough knowledge to understand this problem. Second, we need to work on our first programming project on this topic. So that's why I jump to later chapter. But after this one, most of our remaining material, I will pretty much follow the natural order of the textbook. Okay? Yeah. Yeah. But this one is a little special. Yeah. All right. Yeah. First try. Yeah. We know how to find its value. So that's the straightforward algorithm. You know how to do multiplications. You know how to do additions. We just do that, right? Yeah. There is a natural order for us to apply multiplications and additions. We just do it in that natural way, okay? That so-called natural way, obviously. That's natural, obviously. Anyway, yeah. Yeah. When we do that, we need to work on each term, right? Every time plus you get one term, you need to find the value of that term first before you can do addition, right? Yeah. So here we study a typical term. This is a typical term. A sub k times x to the kth power. Typical term. Okay. Can you tell me how many multiplications do we need to calculate this typical term? How many multiplications? Do the counting. Count number of multiplications. In terms of k, give me the value in terms of k. The expression, you need to use the k expression to give me the answer. How many multiplications? Can you see that? Is it too abstract? Is it abstract? Because this k could be 5, k could be 10, k could be 11, right? Yeah. Is it quite abstract here? Yeah. How to deal with that abstract data? The data is abstract. How to deal with that? Our first problem-solving strategy. Here, I want to introduce it. Problem-solving strategy. Okay? Yeah. So what's that? Here, when you do the counting, we apply a very simple strategy. That is, we do experiments. We do experiments. Okay? Yeah. First, when k equals 1, tell me, we plug in k equals 1. How many multiplications do you need? K equals 1. 1 multiplication, right? Yeah. A1 times x. That's the only one you need to do. Okay, that's one. Then let's try another experiment. When k equals 2, how many multiplications do you need? 2. Simple, right? Yeah. Conclusion. Is it enough to get a conclusion for general k?
Happens every time. The conclusion is that the numbers
Yeah. Is it, if not enough, let's do one more multiplication. When k equals 3, a3 times x to the third, how many multiplication do you need? K equals 3. How many multiplication do you need? Three. Is it enough to get a conclusion?
Yes, the answer is always
It's enough, right? Yeah. So what's your conclusion? Yeah. Okay. Okay. Yeah. This is our first strategy. Okay. Our first strategy. We do experiments on some simple cases. 1, 2, 3. That's simple, right? After you work on some simple cases, you can observe some rule quickly. Right? You can see the rule quickly. All right? Yeah. That's our first strategy. It's simple, but it's effective, right? It's effective. Yeah. So later we need to apply this strategy several times. Okay, get ready for it. Yeah. All right. The question, but is your algorithm efficient? Yeah, because you do this way, each term you get that number of multiplication, but you need to accumulate all the multiplications. Yeah. But when you answer this question, if this algorithm is efficient or not, you don't know, right? You don't know. Why you don't know? Because that's the only way you know how to do the calculation, right? That's the only way. Do you know a second way? To calculate a polynomial, we do not use this way. We want to use a different way. Because most of you, we do not know the second way, right? If there is no second way to be compared with, how do you know the current way is efficient or not? Right? Yeah. One method, you have no comparison for this method. So how do you know it's efficient or not? Okay? Yeah. So in order to know if it's efficient, the first thing, you need to know if there is a second way, a different way to find the polynomial value. Okay? So our next task is, we try to find a different way to calculate this polynomial. Then you can do comparison. All right, yeah. All right, so here, yeah. Because there is another question. When we talk about efficiency question, how do you measure efficiency? Another question, measure efficiency, right? Yeah. Can you use a number to measure efficiency? Yeah, that question. Because when you say efficient or not, without any measure, it's subjective, right? It's subjective, yeah. Okay? Without measure, yeah. So you want some objective way to measure the efficiency, yeah. All right. So the first question, how to measure that? How to measure that efficiency? Okay. Yeah. So here, I raised the question here, okay? Yeah, but we need to answer later. Here, yeah, that's the question. Yeah. All right, all right. Then let's move to the next step. Yeah, if we are satisfied with this, if that's the only algorithm we have, no matter you're satisfied or not, you have to take it, right? If that's the only way, you have no other choices. You have to take it. Okay? So in order to answer if we are satisfied with it, we need to get a second method, second algorithm. Okay? Yeah. Yeah. Then we can do comparison. Yeah. All right. So then the question. So our next question. Can we do the previous computation slightly different? That's something we want to figure out. Okay? We want to figure out. Can we do something slightly different? Because we want to explore the chance. If there is some room for improvement, we want to explore that possibility. Okay? Yeah, if it's impossible, then we get stuck, right? At least we want to see some light. We want to see some light to encourage us. Keep working in that direction. Yeah. So here we want to see something to shed some light to this question. All right. Let's look at x to the k. When we calculate this term, x to the k, can we do slightly different? When we calculate this number, other than our previous way, straightforward multiplication, can we do things slightly different? Yeah, this expression we call a monomial. Yeah. Only single term. Monomial, not polynomial, multiple terms. Monomial, one term. All right. Here, let's take a simple example. Yeah. Here we back to our first strategy. When we consider an expression with the general k, degree k, it's hard to see, right? When it's hard to see, our first strategy, try some concrete number, concrete example, right? The specific concrete example, okay? Yeah. But when we select specific concrete example, we want our example meaningful, right? Yeah. Meaningful, yeah. Meaningful, because x to the first, it's not meaningful, right? Because we do nothing. X to the first, not meaningful, because we do nothing, right? X squared, we do one multiplication, still nothing to do differently, right? Still not meaningful, okay? So we need to select the data k such that this whole expression is meaningful for our computation. Here we select x to the fourth, okay? X to the fourth, this number 4 is not too small to make it meaningful, but not too large, make it too hard, right? Yeah. Somewhere appropriate. Okay? 4, x to the 4th. X to the 4th, can you calculate it differently than our previous way here? Yeah. First tell me, in the previous way, how many multiplications do we need for x to the 4th? Calculate. That's not our previous way, right? Our previous way, yeah, you jump a little fast. Yeah, so we will get there. Yeah, he jumped a little faster than we have. In our previous way, because the a part is gone. A part is gone, right? A coefficient part is 1. 1 means you do not need to do one multiplication, right? Yeah, you can save one multiplication, right? Yeah. So this k number minus 1, right? Because you save one multiplication. Okay? 4 minus 1. So in our previous way, we need a 3 multiplication. All right? Yeah. Okay? Yeah. But now we want to try to find a better way. Yeah. So this is the first multiplication. X times x, we get x squared, the first multiplication. But when we do second multiplication, can we do x squared times x squared to get x to the 4th? We skip x to the 3rd. We skip one intermediate step. Because we already have x squared, can we use it twice? Okay? X squared multiply itself. So one more multiplication, we can get it. So this tells us total we only need 2 multiplication, but in the previous way it's 3. Can you see improvement? Right? So with this simple example, can we see some light? There is a chance we can improve on our polynomial evaluation. We see some light, right? Can we, so here, the reason we can improve, because we find a smart way. We find a better way, right? This is smart way, better way. Can we continue to explore the smart way so that we get much better, more efficient polynomial evaluation algorithm? That's the next question. Okay, yeah. So we see it's possible. Yeah, yeah. All right. So let's go to the next step. Yeah. All right. Yeah. Yeah. So here we move to the next step. Next step. But this time we have a little more confidence, right? Yeah. Because we saw some encouraging example. Yeah. That example quite encouraging. Okay. Yeah. We know there is a hope. Okay. All right. Now, so then work on our current problem. We have more confidence. Yeah. But that's not enough. Even you have some confidence, but you need to get insight to solve the problem, right? You need to find the critical step to solve the problem. You still need to do a lot of work, the critical work. Okay? Yeah. So now we need to get that critical work. Yeah. So what's that? All right. Yeah. Yeah. All right. So here, I just introduced a terminology. That straightforward method is the brute force method. Okay. Before we do any improvement. Yeah. So that one, yeah, our first try, we call it the brute force method. Yeah. Because we didn't apply any technique. Yeah. We just do it in a straightforward way. So that's the brute force method. Okay. So now we want to apply smart technique on it. Okay? Yeah. All right. Yeah. So here we need to consider addition and multiplication. Yeah. The question, yeah. When you need to do an improvement, you have two places you can apply improvements, right? One is reduce the number of additions. Second, reduce the number of multiplications, right? Yeah. Reduce. If you can reduce either one, yeah, you can get better, right? Yeah. So you can get. Still have 30 minutes. Right. Yeah, so we can cover a lot of things in 30 minutes. All right. Yeah. So here, regarding the improvement, what's the room for manipulation? You just change different ways to do manipulation, right? So you need to know your room for the manipulation. So here, the room for manipulation, we apply two operations, addition, multiplication in different order. Do we have freedom to choose different order to apply multiplication and addition? Yeah. Here, I only ask you in the abstract level, okay? Yeah. The concrete level, a little hard, because it's hard to imagine, right? How to do the evaluation in different order is hard to imagine, okay? Yeah. But in the abstract level, yeah, top level, yeah, high level consideration, yeah, by logic, yeah, we can try different order evaluation, right? Yeah. 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 Because we have some freedom to choose different order for evaluation, right? Yeah. Yeah. But for what's that freedom, we need to explore. Okay? Yeah. So theoretically, we can try different order of evaluation. And yeah, all right, yeah, all right. So let's continue. This time, because if you do not do any change, you cannot get a different result. So you have to change something, right? You have to make change to see different results. Yeah. All right. Yeah. So we need to change. Yeah. All right. Then regarding the efficiency measure, remember, yeah. So here. Yeah. So here you can see we spend so much time on the problem understanding. Why we spend so much time? Because we want to understand this problem well. So our discussion, we spend so much time because we are working on understand the question. Okay, yeah. So you collect information everywhere. That's for your understanding. Okay, yeah. All right. So about the execution time, that's the efficiency. So because execution time will tell us if the program runs fast or slow, we can use execution time to see it, right? Yeah. So, but there is one question. If we want to answer efficiency measure, the question, can we use execution time as the efficiency measure? Because in our previous slide, we want to measure efficiency. Yeah. Execution time is a number, right? Can we use execution time to measure efficiency of an algorithm? Think about that. The first question regarding efficiency. Yeah. The answer is no. Yeah. Why is no? Yeah. Yeah. Because the reason, yeah, I saw several students say answer. The reason they said yes, because first, at least it's a objective measure, right? Because you see a concrete number, objective number. But the reason is, the answer is no, is this measure is not stable. If you use execution time to measure efficiency, it's not stable. It can change in different locations, different situations. This number can vary, up or down, not a fixed number. Okay, so why here? Yeah, let me give you the reason it's unstable. Why unstable? Yeah. Because think about, when you run the program, which machine do you use? Do you have an idea? If you use your PC, you can run, but some other people use supercomputer. Yeah. The Google Lab, they have, you know.
So the reason we use execution time is objective abilities because depending on your device, it could be
Yes, yes,
change the result.
yes.
So if you did the same test on two different devices,
Right, right. Because no, you don't specify what machine, right? Nobody can specify what kind of machine to use, right? Yeah. So this is from the hardware point of view, it's not stable. Yeah. Hardware point of view, yeah. Different machine. But from the software point of view, also not stable for software. Yeah. Because for different programmers, even they implement the same algorithm, the result could be different, right? Yeah. Let's think about, you have one particular algorithm. So you ask different programmers to implement. Some programmers, very experienced, they know how to arrange the resource such that they can use the resource very efficient. But for some less experienced programmer, they do not know how to arrange resource efficiently, right? So they do things in an inefficient way, so they may not get the same performance. Yeah. So even from the software point of view, it's not stable. Okay? Yeah. So that means we cannot use execution time to measure efficiency concept. Yeah. Cannot. Yeah. Not a good one. Yeah. Not a stable one. So we want to find some measure that keeps the same on different hardwares and for different software implementations. Always the same number. Yeah. So that's what we need. Stable measure. Yeah. All right. So we will get there. Yeah. All right. So the goal, we want the, stable, same number everywhere. Okay. Yeah. In the above situations, always the same. All right. How to measure efficiency? Here the answer is using the number of additions and the number of multiplications. How about that? That number not related to hardware, right? Yeah. On a supercomputer, you still need to use the same number of additions, same number of multiplications, right? For an experienced programmer, you still need to, because for the same algorithm, you still need to do the same number of additions and the same number of multiplications, right? Yeah. So this number is a much better one, stable one, objective one, and a stable one. Yeah. The counting number. Okay, yeah, question.
So let's say that like if you have a totally different problem where instead of just multiplication you have to compute logarithms or square root, with those different computations have different weight assigned to them based on how complex they are.
Yeah, so you have because your operation is different. Yeah, so the unit time, the time unit you use is different. Yeah, because for each logarithm calculation, time is different. For each square root calculation, it's different. Yeah, it matters. It matters. Yeah, because the square root operation here in computer graphics, the square root operation used a lot. In computer graphics, you move object from one place to another place, right? You need to apply Pythagorean theorem, right? You need to, what's the distance? Move to one point to another point. You need to take square root, apply the Pythagorean theorem. So there are many square root operations. Then you need to measure how much time for each square root operation. Yeah. Yeah. Much slower than multiplication, than division. Yeah. It matters. Yeah. Right. Yeah. All right. Let's continue. For the additions, So here we talk about two different operations. One addition, another multiplication. They are different, right? Yeah. Do you know which one slower, which one faster? Addition and multiplication. We only compare these two. Yes. Yes. Yeah. Actually, it's much, much slower. Not just a little slower, much, much slower. How much? What's the ratio? The ratio is 1-to-10 ratio. 1-to-10 ratio. Okay? Yeah, that's the big difference. Yeah. When you do addition, you use 1 unit of time. When you do multiplication, you need 10 units of time. That huge difference. Yeah. So when we need to look at the overall performance, we need to combine these two operations. So we need to factor in this 1-to-10 ratio. We need to factor in this 1-to-10 ratio. Okay? Yeah. All right.
So under count, instead of using execution time, we would count how many additions you have, and count how many multiplications you have and times it by 10.
Yes. Yeah. So you can do conversion. At the end, for example, each multiplication equals 10 addition. Yeah, you can do that conversion. Okay? Yeah. All right. Here, we want to bridge the gap. So there is this big gap between. Yeah. So we want to do something. So we need to add some assumption, reasonable assumption in this problem to give us some fair way to measure the overall performance. Yeah. Our assumption is, for each addition, we assume 1 unit of time. How about that? Okay. 1 unit of time. Yeah. So the concrete number may not be that important, right? Yeah. The concrete time may not be that important, just 1 unit of time. Okay, all right. Then each multiplication takes 10 units of time. In this way, we can count the number of units of time we need to calculate this polynomial. Then it's a fair way, right? Yeah. You can see it's a fair way to measure the overall performance. Yeah. All right, so let's continue. All right. B.2, estimate the cost. This time we need to really measure the computation cost. Yeah. The time spent, that's the cost, right? Yeah. So not necessarily the money you spend. So the time you spend. Time is money, so time you can convert it to the computation time. Yeah. That's a lot of money, right? Yeah. So here we use the time units we spend for the computation cost. Yeah. All right. Subproblem, the first. Yeah. The original problem, relatively big, so we want to break it into several subproblems. Yeah. Yeah. So we solve subproblems one by one. Yeah. Yeah. The first subproblem, let's count the number of additions. Yeah. Yeah. For this given polynomial. Oh, sorry. Yeah. If we use the straightforward brute force method here, brute force method, can you tell me the number of additions? How many additions do we need? Only additions. Ignore multiplications. Yeah. That's right, but we need a number. We need an expression in terms of n. N, that's the degree number, right? So you tell me the number of additions, give me an expression in terms of n.
10 additions.
10n, why 10n? Why you multiply 10?
Because you know how many multiplications there are.
Ignore multiplication, because remember, we only do subproblem, right? The multiplication is our next subproblem. So now you don't worry about multiplication. We delay it. Only do application problem. How many additions? Yeah. Be careful. Yeah. First, everyone agree there is an n part. Okay. The subtle thing we need to figure out. N plus what? It's possible n plus something, but n plus three cases, let's say. 0, there is 0, right? N plus 0. N plus 1, n plus 2 cases. So which one is correct?
It's just n, right?
Just n. N is correct. N is correct. Yeah. But the question, how do you know n is correct? Because we don't want to make a guess.
Well, because if you have, I mean, what you can see right here, if you just counting A0, you don't see any additions. And when you get to A1,
Yeah.
you have 1 addition. So
Yeah.
you can see
Good.
that it's linear.
Good, I understand. He used the induction method. Yeah. He used induction method. What's that? He started with n equals 0. When n equals 0, you only have A0 term, right? Then no addition, 0 addition. Then he started with 1. A0 plus A1, 1 addition. That is A. Then this is called induction. Oh, we do experiments. This is just like our strategy, experiment strategy. Okay, you plug in, yeah, that's effective. So good one. Now, he made his conclusion based on induction observation. All right. Here, I want to introduce you another counting method, basic counting method. When you do counting, so here, when you look at this formula, when we count the number of addition, first, by your observation, is it 1 plus sign corresponds to 1 addition? 1 plus sign corresponds to 1. If you see certain number of plus sign, you will get the same number of additions, right? Is that observation correct? The number of additions equal the number of plus signs. Plus signs. That's obvious, right? Because plus sign means one addition, right? Yeah, that's obvious. Okay, all right. The question, how do you keep track of plus sign, right? Because when we count the number of plus sign, at least we need to keep track of the data, right? Yeah. Plus sign. So my next question, how do you keep track of the plus signs? Is there a convenient way to help us keep track of the plus signs? Yeah, yeah. Right. That's the induction method he used. Now, here we want to take a different way. Here we do not use the induction method. Well, because here, our question, we want to keep track of the plus signs. Okay, it's a different question. Yeah. All right? Yeah. So here I introduce you a new method, new counting method. So I call it counting by reference. Counting by reference. That's based on our everyday life experience. In your everyday life, do you use reference a lot? When you get to a new location, new place, you are not familiar with a new city. So you need to use different references a lot, right? You know, a building, a tower, you know, some traffic light. That's what we treat as references, right? The third traffic light, for example, is that a reference? Yeah. Here we want to use the similar reference. So here, we're in a new place. It's hard to keep track of some objects, right? The plus sign, that's the objects. But hard to keep track of plus sign objects. So we need to use some simple, easier, different objects, but easier to identify to help us locate those hard objects. Yeah. So that's the idea. So we use reference. All right. Yeah. So here, the problem solving strategy. So we work on easier parts first. Yeah. All right. So here, when we do the counting, dot, 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 hard to keep track of. Dot, 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 we get lost. Right? Dot, dot, dot. Okay? All right. So how to find an effective way to keep track of those invisible terms? There are many invisible terms. Okay? Yeah. How to keep track of? Yeah. So the idea is find appropriate reference objects. Appropriate reference objects. Yeah. So that's we use counting by reference. But you need to find appropriate reference objects here. Okay? All right. The essence of method. We want to discover one-to-one correspondence between two mathematical objects. Right. One object, plus sign is a mathematical object, right? But what's the reference? You know the pattern? Yeah.
So it starts at 0, right?
Yeah.
The subscript, when the subscript increases, it's also the amount of plus signs.
Right. Yeah.
So you can use the subscript of the number to figure out the amount of plus signs that are.
Yes.
So
Yeah.
A subscript 1 plus.
Correct. Yeah. Correct. He gave the reference object. What's the reference object? Subscripts. Subscripts, clear, easy to identify, right? Subscript, the first one, second one, easy to identify. But plus sign, hard to identify, right? Yeah. So you use the object that are easy to identify to describe object hard to identify, plus sign. That's the idea, yeah? All right, so here I use this diagram to describe this idea. We have object 1, object 2. Okay, you need to find object 2. Yeah. Object 1 given. Yeah. But you need to search. You need to find appropriate reference. Object 2. Okay. All right. But after you find that, you need to establish one-to-one correspondence. One-to-one. Yeah. All right. Because Usually object 1 is hard to count. Hard to keep track of it. So hard to count. But object 2 easier to count. After you establish one-to-one correspondence, okay? Yeah. After you establish one-to-one correspondence, then the number of object 1 should be equal to the number of object 2, right? Because one-to-one correspondence. Okay? Yeah. Yeah. So then you only need to count object 2 instead of object 1. That's easier, right? So let me use this question to explain this method, counting by reference method. Okay? Object 1 is a plus sign. Object 2, a subscript. Okay? One-to-one correspondence, then one-to-one correspondence, yeah. So from what you said associate 0 with first plus sign, right? Yeah. Yes, yeah. But we can also, how about we associate 1 with the first plus sign? Also, it's okay, right? Yeah, 1-to-1, because it's 1-to-1. 1-to-1, if we associate 1 with plus sign, then we exclude the first term. Yes, yes, yes. So in this way, the last plus sign, we associate this last subscript, okay? Yeah, and so here you can see, yeah, when we do counting, because the subscript is from 1 to ... to n, you count the number of objects here, that's easy, right? N consecutive integers. That ... you won't get lost, right? 1 to, when you, because they are consecutive integers. When you see ... you won't get lost, right? Yeah. But you see ... here, you may get lost, right? How to keep track of it. Yeah. So that's the difference. Yeah. So the object 2, when you do the counting, you won't get lost because they're consecutive integers. Okay? Yeah. So now you do that switch. Okay? Yeah. So you can get a correct counting number better, right? Yeah. Yeah. So that's another counting method. Yeah. All right. So here, the answer, now you know the answer. Yeah. So that's n. Yeah. All right, we solved the first subproblem, second subproblem. This time we need to count number of multiplications. Yeah. Yeah. All right. But when we count number, each term, we did it before, right? Yeah, from the, we already get the answer, k. Now, you need to accumulate multiplications from all the terms. Yeah. Yeah. All right. Yes. So let's do that accumulation. Okay. Yeah. There are n plus 1 term, but the first term there is no multiplication contribution, right? A0 has no multiplication contribution. Okay. All right. So let's do the chart. Yeah. Yeah. A1x, this term has 1 multiplication contribution. Okay. The next term 2 contribution, 3, and so on. The last one n multiplication contribution. Okay. All right. So the total number adding up, the first consecutive positive integer from 1 through n. What's that formula? Do you know that formula? There is a formula for that. Yeah. A famous formula. Yeah. Very famous formula. 1/2 times n plus 1. Yeah. 1/2 times n plus 1. That's the formula. Okay? Yeah. You need to memorize this. Yeah. The basic formula, yeah, commonly used. So yeah. All right, yeah. So then here we know the number of multiplications. This is the final number of multiplications. Okay, yeah. Yeah. All right. Subproblem number 2. Now, question?
Can you also use summation, like the sigma?
Yeah, summation, sigma. Yeah, so that's the, right. Yeah, this one, you can use summation, but that's a notation, right? That's a notation, yeah. He's asking that we use summation I from 1 through n. Yeah, so that's a notation, okay? Sigma, notation, okay? Yeah. But the formula you need to memorize it, right? Yeah. All right. Then total units. Remember, 1 multiplication equals 10 additions. We need to convert it to the number of time units, right? Yeah. So the units, how to do the conversion? N additions correspond to n units of time based on our assumption, right? Yeah. But we have this many multiplications. Each multiplication 10 units of time. So you need to multiply 10, you get this many units. Yeah. All right, yeah? So we get total units. All right, next time, so we will try to improve the total number of units. Okay, all right, so we finish 2 subproblems, but we have a lot of work to do. So we want to improve our evaluation method next time. All right, that's it.